Where did my thing go? Of course, my thing is closed now. Because why wouldn't it be? All right, give me just 1 second. I got to open up the Prelab. For some reason, mine closed, even though I had it ready this morning. That's been the way that everything's been working lately. Okay, I'm going to present now. Where did my thing go? Gosh darn it, it was just there. Okay, I think I have too many things open. Because it just closed out my stuff again. This is the third time I'm doing this. Okay. Surely but slowly. All right, so we're going to start looking at page 3 on the Prelab right now. And what I have here is some sample data. So the data I've been giving you guys for rate loss so far is like precise data. It's not actual lab data. All of those numbers are pretty and it's easy to calculate the order, like 2 to the x power is equal to 4, x is equal to 2, or 5 to the x power equals 25. X again is equal to 2 because 5 squared is 25. So you guys have been getting pretty numbers that way. In the lab, you don't always get the pretty numbers like that. So the way that you would figure out your order with respect to that reactant is by using logarithms. So in the Prelab, these practice problems we're going to go through, you're going to see this on the lab that we do next week. This weekend, I'm going to videotape myself doing the lab. You guys are going to record your numbers and do the calculations based on the lab data that I collect. So that's why you'll be seeing these sorts of calculations again. So the lab data that you see here is in the chart. And I'm going to go ahead and kind of walk you through the problems. So the first set of problems we're going to do is for nitrogen monoxide. We're going to calculate the order for NO. And in doing that, we're going to look at dividing what it tells you here, reaction 4 and reaction 5. And we're going to see this when O2 is kept constant. So you can see that O2 is constant in reaction 4 and 5, but NO is changing. The concentration of NO is 0.040 and for reaction 4, and for reaction 5, it's 0.010. That's going to be to some x power. That's the order that we're trying to find. Now we're going to divide the two rate values. So for 4, it's 0.230, and for 5, it's 0.0140. Simplifying that out, so cleaning that equation up there, we get 4.0 to some x power, 0.230 divided by 0.0140 is 16.4. So most of you could look at that and say, okay, x is probably going to be 2 because 4 squared is 16. But we're going to try to get exact values here. So the way to calculate x, it's going to be the log of the number on the right, 16.4, divided by the log of the number on the left, the one that you're bringing the power to, the log of 4.0. When you type this into your calculator, you're going to have to use parentheses. When I type it in, I say parentheses log parentheses 16.4 and then parentheses divided by log parentheses 4.0 parentheses. So close those. If you don't do the parentheses all the way on the top when you're dividing, you won't get the right answer. So if you guys want to take a second and type that into your calculator, I want you to compare it to the answer that I get here. So when I type it in, I get 2.0178, okay, and then some other numbers after that. So hopefully that's what you get when you're typing it in. Now, when we write an answer with sig figs, with logarithms, it's different. Your answer is going to have as many decimal places as the fewest number of sig figs. So 4.0 only has 2 sig figs. That means my answer will have 2 decimal places. So it's going to end up being 2.02 there for my order with sig figs. So I'll explain that again as we continue on with these problems here. All right, so now we're going to look at reaction 4 over reaction 2, and we're going to be focusing on nitrogen monoxide's concentration still. So nitrogen monoxide's concentration there is 0.040, and the rate value is 0.230. For reaction 2, its concentration is 0.020, and its rate value is 0.0562. Now the concentrations we're going to bring to the x power, and then we're going to simplify that. And when we simplify that, we get 2.0 to the x, and then 0.230 divided by 0.0562 is 4.09. Again, to find the x value, we're going to take the log of the number on the right, so the log of 4.09, divided by the log of the number on the bottom, the log of 2.0. When we type that in, I'm going to type in parentheses, log, and then the parenthesis there shows up, 4.09, and then parenthesis, divided by the log of 2.0, and then close that parenthesis. And you should get, again, 2 sig figs is the fewest sig figs, so my answer is going to end with 2 decimal places. That comes out to be 2.03. For the final calculation there, we're going to compare reaction 2 divided by reaction 5, focusing on nitrogen monoxide's concentration. So for reaction 2, nitrogen monoxide is 0.020, and for reaction 5, its concentration is 0.010. Reaction 2's rate value is 0.0562. Reaction 5's rate value is 0.0140. My concentrations, I'm going to divide them and bring them to some x power. So 0.020 divided by 0.010 is 2.0 to the x, and 0.0562 divided by 0.0140 is 4.01. To solve for x, I'm going to take the logarithm of the number on the right, 4.01, divided by the log of the number on the left, 2.0. 2.0 is my fewest number of sig figs. That has 2 sig figs in it, so my answer will have 2 decimal places. That comes out to be 2.00 on the nose. So now I need to find out what the average order of nitrogen monoxide is. I'm going to do that by adding my 3 orders there and dividing by 3. So that's what we mean by average order. So 2.02 plus 2.03 plus 2.00 comes out to be 6.05. Divide that by 3, and my X value, my average order, is 2.02. That would give me an order rounded to the whole number of 2, which means that my reaction with respect to nitrogen monoxide is second order. Okay, so I'm going to give you a second. My pluses look terrible there. I'm going to give you a second to write anything down in case you need that. And I'm going to go back to the meeting real quick. Well, actually, shoot, I'm not going to because I don't see this on my screen. I don't want to lose it again and have to start all over. So once I'm done here, I'll go back to the meeting so that way I can answer any questions you have. All right, now we're going to look at oxygen's order. So we're going to do that by the same process that we did with nitrogen monoxide, but this time we're going to concentrate on oxygen's concentration. So reaction 3, oxygen's concentration is 0.040. And for reaction 1, its concentration is 0.010. We're going to bring that to some X power. The rate for reaction 3 is 0.110. And the rate for reaction 1 is 0.0280. That's a really bad looking 8, sorry. Simplifying that, 0.040 divided by 0.010 is 4.0 to some X power. And 0.110 divided by 0.280 is 3.93. Using logarithms to solve for X, it's going to be the log of the number on the right, 3.93, divided by the log of the number on the left. So the log of 4.0. When we type that in, again, make sure you're closing your parentheses for the logarithm on top. So it divides by the log of 4.0 on the bottom. So if you type that one in correctly, and I'm going to retype this so I can kind of compare the numbers to you guys. I get 0.98726 and a bunch of other numbers after that. Now, my fewest number of sig figs here is the 4.0. That's 2 sig figs. My answer will have as many decimal places as sig figs. So my answer is going to round to 2 decimal places, which comes out to be 0.99. You have 0.987, which would round up to 0.99 there. Looking at the next reaction there, we're going to take reaction 3's concentration of O2, 0.040, divided by the concentration of O2 for reaction 2, which is 0.020. Bring that to some X power. That is going to equal the rate of concentration, or not, sorry, the rate of reaction 3, 0.110, divided by the rate of reaction 2, 0.0562. Cleaning this up, 0.040 divided by 0.020 is 2.0 to some X power. And then 0.110 divided by 0.0562 is 1.96. So my X then is going to be the log of 1.96 divided by the log of 2.0. And in calculating my logarithm there, again, make sure you're using parentheses. So close the parentheses for that number on top, the log of 1.96 divided by the log of 2.0. Here, your fewest number of sig figs is 2, so your answer will have 2 decimal places. 2 decimal places should round to 0.97. Looking at the last one here, reaction 2 has a concentration of 0.020 for O2. And for reaction 1, oxygen's concentration is 0.010, brought to some x power. That is going to be equal to the rate of reaction 2, 0.0562, divided by the rate of reaction 1, 0.0280. 0.020 divided by 0.0010 is 2.0 to some x power. And that is going to equal to 2.01. So then x is going to be the log of the number on the right, 2.01, divided by the log of the number on the left, 2.0. X here comes out to be 1.01. Now we're going to take an average of those three numbers again. So 0.99 plus 0.97 plus 1.01. That there came out to be 2.97. Divide that by 3. My answer here has 3 sig figs because I'm going to leftmost uncertainty, the hundredths place. And 2.97 has 3 sig figs, so that rounds out to be 0.990. So x, rounding it to a whole number, would be 1, which means it's first order with respect to oxygen there. So writing my rate law expression, all rate law expressions start with rate equals K. For nitrogen monoxide, NO, we got that to the second order or second power. And for oxygen, we got that to the first order or first power. So that's what my rate law expression would look like. The overall rate order for the reaction is the sum of your exponents. So 1 plus 2 adds up to 3. So it's third order overall. And then calculating the specific rate constant, this is the hardest part of the whole problem. You're solving for K. So to get K by itself, I have to divide by nitrogen monoxide and oxygen. So it's going to be the rate divided by nitrogen monoxide squared and oxygen to the first power. Always use the trial 1 data to keep it consistent for that. So I'm going to kind of scroll down here so I have some room to work. So K then would be the rate for trial 1, which was 0.020280 rather. And your units for rate here are different than our problems. It's a 1 over a second instead of molarity per second. Nitrogen monoxide's rate 1 concentration is 0.020 molar, and that is squared. And then for oxygen, it's 0.010 molar, and that is to the first power. When you're solving for this, you gotta square 0.02 first, and then multiply it by 0.010. And when I do that, what I get is 0.0280, 1 over second, divided by 4.0 times 10 to the negative 6. A molar squared times a molarity is a molar cubed. So dividing those two numbers, I get 7,000. I believe that's what I got. Let me double check. Yeah, I got 7,000. Now, the only way we can show 7,000 with 2 sig figs is scientific notation. So 7.0 times 10 to the third. Now, you have a 1 over a second divided by molarity cubed, which is the same as multiplying by its reciprocal, 1 over m cubed. So your final unit then for this ends up being a 1 over m cubed times s. So units are a little bit tricky to calculate. I've been trying to walk you through that and show you that a whole bunch there. All right, I'm going to return to the meeting and stop presenting. And let's see here. I'm also going to stop recording.